Good afternoon or evening, AP Calculus students. So this is my first video for the Unit 1 review packet, right? So I'm releasing each of these videos. They're each 7 points. They're actually critical for you to get done in order to pass fourth quarter, and obviously critical for you to do and redo in order to prepare for the AP exam. So what I'm going to do is basically use this as a video guide / video answer key for every AP problem. So you'll notice this problem right here is labeled AP. So we're going to go through every single one. Now you can obviously copy it, but I want you to basically ideally what you should be doing is attempting the problem. Then if and only if you get stuck, consult this as a guide. And when you do, follow it carefully so you can figure out how to actually do each problem. All right, let's look at this first one. So the figure above shows the graph of the function f. Which of the following statements are true? All right, so it's a bunch of limit statements. So you'll see limit as x approaches 2 from the left is equal to f of 2. All right, so let's first figure out what is a limit. So definition of a limit, right? We have certain definitions, right? A limit, as let's say x approaches, limit as x approaches I'm actually going to use symbol lab. So limit as x approaches, let's say, a number a. Well, what does this mean? That a limit exists if the limit as x approaches a from the left is equal to the limit as x approaches a from the right. All right. So basically, for a limit to exist, it has to come to the same point from the left and the right. All right. So let's see which of these statements are true. Well, this says the limit as x approaches 2 from the left is equal to f of 2. Well, let's take a look and see if that is true. So the limit as x approaches 2 from the left. So I'm approaching 2 right here from the left. So that is going to -1. So this one's -1. All right. What is f of 2 exactly? Well, if I go to f of 2, so that means this is the exact value. Right? I just jump straight to 2. If I jump straight to 2, you'll see I have a dot right here. That is also just -1. So this statement is saying -1 is equal to -1. Is that true? Yes, that's obviously true. So I'm going to put a check mark. All right. Now, let's see. This says the limit as x approaches 6 from the left. So I'm approaching 6 this time from the left. The y value is -1. So it's -1 is equal to limit as I approach 6 from the right. So I'm approaching from the right. This time I'm coming from the right. That's also equal to -1. Right? It's approaching the same point, the same y value. So -1 is equal to -1. Excellent. That is correct. All right. Final one. It says the limit as x approaches 6 is equal to f of 6. All right. And now here's where we use my definition. What is the limit as x approaches 6? Well, remember, the limit as x approaches a specific value, let's say 6 in this case instead of a, means that the limit as I approach 6 from the left has to be equal to the limit as I approach 6 from the right. Well, is that true? Let's see. So I approach 6 on the left, and I approach from the right, and they are equal to each other. They're approaching the same point. So this is true, and it's equal to -1. So that's great. My left side is fine, and it's equal to -1. Okay, how about this right side? F of 6. Is it equal to f of 6? Well, I'm going to jump straight to 6, and you'll see this is actually an empty circle right there. My actual value here is down here at this filled in circle. The exact value is -3. So is -1 equal to -3? Obviously not. So 1 and 2 are correct, but 3 is not true. So my answer choice is going to be C, 1 and 2. All right, hopefully that makes sense. Let's jump to the next AP problem. All right. So still with limits, this says the limit as x approaches 3 from the left is which of these values? Well, how do I solve limits? All right, so we moved on from definition of the limit. Now we're going to take some notes on solving limits. Right. Now, solving limits, we have a few methods, right? the first method, the most direct method for solving limits, is called direct substitution. Right, so let's try that. I'm going to plug in 3, right? This says 3 from the left, but basically I'm approaching 3, so let's plug in 3. So it's going to be the absolute value of 3. So it's going to be, instead of x minus 3, it's going to be 3 minus 3 divided by 3 minus 3. All right, you'll see Desmos actually gives me an answer here. It's undefined. Well, the issue is that this gives me a 0 divided by 0 answer. Am I allowed to do that? No. Cannot divide by 0. Okay, so I cannot do method 1. All right, now method 2 is some sort of algebraic manipulation to see if I can cancel stuff out so I don't have to divide by 0. Can I cancel anything out? I almost could. It would almost be equal to 1, but there's absolute value bar, so I can't cancel out x minus 3 directly. So I cannot directly cancel it out. All right, so you'll see this is in the category of vertical limits at an asymptote, because method 3 is basically what to do at an asymptote, right? And the method directly is this: plug in values close to the asymptote to see if it's going to positive infinity, negative infinity, that sort of stuff. So that's exactly what we're going to do here. I'm going to plug in a value that's close to 3 from the left. So what value would that be? I'm going to choose from the left, I'm going to choose 2.99, right? And I can think about it this way. All right, so I plug it in. The top is going to be absolute value of 2.99 minus 3. The bottom is just going to be 2.99 minus 3. This is equal to negative 1. And you might say, why is it not just positive 1, right? Well, remember, 2.99 minus 3 would normally be negative 0.01. However, it is absolute value, so it turns into positive 0.01, right? Now, the denominator is just our normal negative 0.01. So 0.01 divided by negative 0.01, that's equal to negative 1. Right, so my answer is B, because I exhausted all my methods of solving limits. Direct substitution didn't work. Algebraic manipulation didn't work. So method 3, there's an asymptote, so I just plug in values close to that asymptote. So that's how you would solve this. Cool. Let us move on to the next question. All right. Let f be a function of x if the limit as x approaches 2 from the left is equal to infinity and the limit as x approaches 2 from the right is equal to infinity. Which of the following could be the graph of f? So this is what it's saying. I know the writing is small, so let me write it out. Limit as x approaches 2 from the left is equal to infinity. The limit as x approaches 2 from the right is also equal to infinity. So what are they saying exactly? Basically, they're saying, let's say I have a value 2 here. From the left, as I get closer to 2, my function just goes straight up, right? It's going to infinity. So it's going to go like, boom. It's going to a y value. Remember, limits, these are all y values. Infinity is a y value, right? From the right, the same thing happens. I'm coming in from the right, but boom, I go straight up because I'm going to infinity. All right, this graph that I just drew looks like what? Well, it's going to look like D. That's my answer choice, right? It's clearly not going to be the other ones. For answer choice A, this approaches a finite value, right? It stops here, so it's not going to be infinity. This one goes to positive infinity and negative infinity, right? This one goes up and down. This one does the reverse, down and up. Only answer choice D, both of them from the left and the right, they go to infinity, right? Hopefully that makes sense. Okay, cool. Next, we're going to do basically one of our final types of limits, which is solving limits at infinity. So let's go to the first AP problem. Right, so limits at infinity. This is the next section of like new notes that I would take. All right, limits at infinity. What is our method for this? Well, our method is to circle the dominant term in the numerator and numerator and denominator. You can literally ignore everything else. You can actually do that. So first problem here, the dominant terms, fortunately or unfortunately, there's only one term. So in the numerator, it's going to be x cubed. In the denominator, it's e to the 3x. There's no other terms. All right. Cool. So after that, so I guess I would say this is step 1. So I'll say 1. You ignore everything else. The next step is you compare those two terms. So I'm going to compare x cubed and e to the 3x. All right, which one is more dominant? Well, there's a few ways you can think about this. First, you can reference your notes, and you'll notice e to the x, e to some x value is more dominant than, this is x cubed, it's more dominant than x to some number value, right? So which one's more dominant? It's going to be e to the 3x. Now, another way to think about this is e to the x is much greater than x cubed, right? Because with e to the 3x, the exponent is literally going to infinity. This has a much bigger impact, right? Here, the base is going to infinity, but the exponent's just always going to be 3. In this case, the exponent is going to infinity. It's going to increase at a crazy amount, essentially. So the denominator is more dominant in this case. When the denominator is more dominant, 3, so this is sort of the third step. If denominator is more dominant, the limit goes to 0. It's going to go to 0. So my answer choice is A. And remember, this occurs because it's essentially the denominator is more dominant. It's a really large number. So you can imagine something small divided by something huge, right? It's gigantic. You could see how this would be like a very small number. So it's going to go to 0. All right. Hopefully that makes sense. All right. Next question. So this is one I gave very few. So probably should have spent more time on this in class. So I only sent out notes for this. But they ask for a horizontal asymptote. So I'll say we should have taken some additional notes on this. How do I find a horizontal asymptote? Well, to review, my method is this. You take the limit going to infinity. That's it. So basically what we just did, you take the limit going to infinity. This gets you your horizontal asymptote. All right, so the line y equals 5 is a horizontal asymptote to the graph of which of the following functions. So basically 5 is my horizontal asymptote. That means what? Well, that means, like I said, the limit as x approaches infinity of my function is equal to my horizontal asymptote. Well, what do they say my horizontal asymptote is? It's 5. All right. So this is true for which one of the statements? Right? Which one of these functions is this true for? Well, let's take a look at this first function. Right? Okay, my first function is sine of 5x divided by x. First, well, there's only one term, so which one is more dominant? X is more dominant because x actually increases. Sine, remember a sine wave, it just goes back and forth, so it never increases. So x is more dominant, which means the limit is 0, right? Because the denominator is more dominant. All right, next one, 5x. Well, there's only one term. If I were to say there's only a numerator, right? So 5x is more dominant, right? There's not even a denominator, right? You could write it like this, 5x divided by 1. So 5x is my numerator, 5x is more dominant. The limit is infinity if the numerator is more dominant. All right, next one, 1 over x minus 5. Well, which one's more dominant? It's obviously not going to be 1. X minus 5 is more dominant. Or actually, in this case, let's write this out. First, I just focus on my most dominant terms, which is 1 and just x. Right, so I can actually eliminate the 5. Just ignore the 5. So it's 1 over x. x is more dominant. If the denominator is more dominant, that means the limit is 0. Cool. So far I've not gotten 5 yet. Remember, I want to get 5. All right. Next one, 5x is the most dominant term, and also negative x is my most dominant term. So 5x divided by 1 minus x. My most dominant terms in the numerator and denominator are going to be 5x and negative x. Between these two, which one's more dominant? Well, actually, they both have x, so they're equally dominant. So I can cancel those out. 5 divided by negative 1. So negative 5. My limit is negative 5. Limit is negative 5. All right. Well, I'm close, but I'm looking for positive 5, right? So it's not going to be this answer choice either. Final option, E. So it better be E. If you're doing multiple choice, you could probably just choose E at this point because you've eliminated all the incorrect answers. But let's look at this. So I'm going to type this out. 20x squared minus x divided by 1 plus 4x squared. All right. On the top, which one's the more dominant term? It's 20x squared. So I can ignore everything else. On the denominator, it's 4x squared, so I can ignore everything else. Cool. Between these two, which one's more dominant? Well, x squared and x squared, they're actually equally dominant, right? So I can cancel those out. So 20 divided by 4. This simplifies to just 5. This is what I'm looking for, so my answer choice is going to be E. E is the correct answer. My horizontal asymptote is 5. Remember, because my limit going to infinity is 5. Okay, hopefully that makes sense. Let's move on to the next problem. All right, this is later on in the year, but it is a limit, so I decided to include it in this section. Okay, so let's take, first of all, what rule is this? L'Hopital's rule. So actually, let's take some notes on this. L'Hopital's rule. What is the rule? Well, try to recall this in your head, but basically the rule is if and only if my limit is equal to 0 divided by 0 or infinity divided by infinity, then I can apply L'Hopital's. Right, so if and only if my limit is equal to 0 over 0 or infinity over infinity, if my limit is equal to like 5 divided by 0, I cannot apply L'Hopital's. This would be a vertical asymptote, so I would have to use my vertical asymptote method. All right. So what is the actual rule? The rule is the limit. Actually, I'm going to write this here. I'm going to write my limit here. The limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f prime of x divided by g prime of x. So basically, I take the derivative of the top and bottom. Basically, derivative of numerator and denominator. Then retake the limit. Right, so I'll take the derivative of the numerator and denominator, then retake the limit. Remember, I can only do this if and only if my limit is equal to 0 over 0 or infinity over infinity. So hopefully you have this down for your notes. Let us do the problem then. Okay, so here's my problem. The limit as x approaches 2 of ln of x plus 3 minus ln of 5 over x minus 2. So I don't even know to apply L'Hopital's right now, right? I'm just approaching this limit like sort of raw. Like my first method is going to be direct substitution. Right? I have to prove that I can use L'Hopital. So to start off, I need to use direct substitution. So to do that, I plug in 2. So ln of 2 plus 3 minus ln of 5 divided by 2 minus 2. All right, you'll see it's undefined. Let's actually be more precise. 2 minus 2 is 0. ln of 5 minus ln of 5, that's also equal to 0. So it's 0 over 0. This allows me to jump to my L'Hopital's rule. So I'm going to say, now I can apply L'Hopital's rule. Right. So what is my rule again? Well, instead of the limit of just f of x over g of x, I simply take the derivative of f of x and the derivative of g of x. So let's take the derivative. Well, derivative ln of x plus 3, that's going to be 1 over x plus 3, right? Minus derivative of ln of 5. Well, ln of 5 is just a number, right? It's like any other number. So it's like any other number like 3 or pi or -7. What is the derivative of a number? Well, it's going to be literally just 0, right? So it's -0. All right, cool. So I took the derivative of the top, took the derivative of now the bottom derivative of x minus 2 is just going to be 1, right? And I'm going to retake my limit. So remember, I did the derivative, but I'm going to retake my limit as x approaches 2 of this function, right? So here, let's simplify this function. That's really 1 divided by x plus 3. That's it. This simplifies to 1 divided by x plus 3, right? Because the 1 is unimportant, and then the 0 also, I can just get rid of it, right? So it's 1 over x plus 3. Well, how am I going to solve this limit as x approaches 2? Well, I go back to my limit methods, and my method 1 is direct substitution. So direct substitution of 1 over x plus 3, that's going to be 1 divided by 2 plus 3. That is simply 1/5. That means my answer choice is going to be B. All right, hopefully that makes sense for this problem. All right, let's keep on going. These other two are also going to be L'Hopital's problems, but remember, I don't know that for sure yet. So my first method is direct substitution. So I'm going to plug in -3 for x. So it's going to be f of 2 times -3 minus 1 divided by -3 squared minus 9. All right, well, let's solve this. The denominator is going to be 9 minus 9, so I already know that's going to be 0. Let's look at the top. F of 2 times -3 minus 1, that is f of -7, right? And if I go to my table, I'm going to use my table. F of -7 is 0. So it's 0 over 0, which means, remember, why is this important again? Oh, sorry, f of -7. So it's 0 over 0, which means I can use L'Hopital's rule. I can use L'Hopital's rule. All right, so what is my L'Hopital's rule? Well, instead of taking the limit of this, I take the limit of the derivative of the top and the derivative of the bottom. So let's do that then. Let's start with the bottom because this one's easier. What's the derivative of x squared minus 9? That is just going to be 2x. All right, derivative of the top here. Well, derivative of f of 2x minus 1, I don't really know that the function, the derivative is just going to be f prime, right, of 2x minus 1, right? However, I do know this function has an inside function, so this is a chain rule. So I need to multiply by the derivative of the inside. So I'm going to note it. No, this is a chain rule. Right, so I took the derivative of the outside. I need to then multiply it by the derivative of the inside, so I multiply it by 2. All right, so now I did this, right? So I need to take the limit again. So I'm going to take the limit as x approaches -3 of this function. All right, so cool. I have a new function to take the limit of. What's my method again? Well, we sort of go back. My method 1 again is direct substitution. So let's retry direct substitution. All right, so I'm going to plug in -3. So it's going to be f prime of 2 times -3 minus 1 times 2 divided by 2 times negative 3. All right, let's just continue and solve for this. Well, the denominator is going to be negative 6. The numerator is going to be f prime of negative 7 times 2. All right, denominator again is negative 6. The numerator, f prime of negative 7, how do I solve this? Well, I go to my table. F prime of negative 7 is positive 6. So it's going to be 6 times 2. All right, 6 times 2, that's 12, divided by negative 6, that's going to be negative 2. So my answer choice is B. Excellent. Cool. Hopefully that makes sense. Let us go on to the next few problems. All right, L'Hopital's rule. This one's also going to be L'Hopital's rule, this next problem. However, we don't know that, right, to start off with. So I'm approaching this function. What is my method supposed to be? Well, method 1 is direct substitution. All right, so x is approaching negative 5, so I'm going to plug negative 5 into my function. So it's going to be f of negative 5. I plug in negative 5 for x right here. Cool, the denominator is going to be 3 times negative 5 plus 15. All right, let's figure out what this is equal to. Well, the denominator, 3 times negative 5 plus 15, you'll see that equals 0. f of negative 5. So first, I'm going to solve f of negative 5, this inside part. Well, what is that? F of negative 5 is negative 3. Right, so it's going to be f of, I solved it for negative 3. Okay, cool. What is f of negative 3 now? Well, f of negative 3 is 0. So it turns out to be 0 divided by 0. Hint, this means I can use L'Hopital's. All right, so let's apply L'Hopital's. Remember, L'Hopital's means instead of this function, I'm going to take the derivative of the top and the derivative of the bottom. Instead of this, I take the derivatives of each. Well, let's take the derivative first of the bottom. Let's say 3x plus 15, the derivative of that is just 3. All right, derivative of the top, this is again a chain rule, right? Because there's an outside and an inside function, chain. So derivative of the outside is just f prime, and I leave the inside the same, so f prime of f of x. Then I multiply by the derivative of the inside, so I multiply by derivative of f of x is just f prime of x. All right, so that's my chain rule. Now, remember, I'm going to take the limit of this function. I'm just going to redo my method 1, which is direct substitution. So it's the limit as x approaches negative 5 of this function. All right, so let's resolve this limit. So it's going to be f prime of f of negative 5 times f prime of negative 5 divided by 3. All right, so I plugged in negative 5, I directly substituted, now it's just time to solve. So the denominator is 3. The top, f prime of f of negative 5 is what? Well, I go to, I'm going to erase these. So f of negative 5 is negative 3. So it's going to be negative 3 times f prime of negative 5. Well, f prime of negative 5 is negative 1. So it's times negative 1. Cool. So this is negative 3. F of negative 5 was negative 3, but I need to solve another layer, right? So next step, I need to solve f prime of negative 3. Right? There's like 2 layers of functions. So f prime of negative 3 is 9. So it's going to be 9 times negative 1 is equal to divided by 3. So that's equal to negative 3. My answer choice is going to be B. All right. Hopefully that makes sense. Cool. We're going to move on now to continuity. All right, so this is my first problem. And before I tackle my continuity question, let's take some notes on continuity. So what is continuity? Definition of continuity. Well, actually, this is great because we're building on my definition of limits. So if you remember, my definition of a limit is that, actually, I'm going to write this over here. Oops. All right, definition of continuity. So if you remember, my definition of a limit is that as I approach from the left of a function, it must be equal to as I approach to the right of a function. The limit from the left and the right must be equal, right? The one added caveat for continuity is that it must also equal the exact value. So f of a. So three things have to be equal to each other. And you'll note that is in my notes right here. So the limit from the left must equal the limit from the right, and it must equal the exact value. So really, from the definition of a limit, we added one thing, which is just this. That's the one addition that takes it from the definition of a limit to the definition of continuity. All right, so there's just one extra step. All right, well, let's apply this limit definition. So I'm going to write limit from left must equal limit from right must equal the exact value to put it into words. All right, so the graph of a function is shown above. The limit exists, but it's not continuous at x equals a. Then what is a? So what are they saying here? They're actually saying this. They're saying that this is true. The limit from the left is equal to the limit from the right. But what's false is when I add in that extra step. When I add in the extra step, that it's equal to the exact value. So there's some point on the graph where the limit from the left is equal to the limit from the right. But it is not going to be equal to the exact value. So let's see where that happens. Well, I'm going to start just looking at this graph and look at some points. So here at -1, right, this is -1. Let's see, limit from the left is not equal to the limit from the right. So it's actually not going to be -1 because this is not even true for that. The limit from the left is not equal to the limit from the right. All right. Let's look at the next point. So let's look at 0. So the limit from the left is equal to the limit from the right. Actually, that's also not true. The limit from the left is going to 3. The limit from the right is going to 4. So it's not going to be this either. All right. Next one, C. The limit from the left is going to 2. The limit from the right is going to 2. Okay, cool. So this is true. So good. That part is true. However, I need to make sure that this is false because they're asking me to find a point where it's not equal to the exact value. Well, what is my exact value? My exact value is 1. Great. So this is false. It is not continuous, right? So it's not continuous because from the left, basically this is saying it's 2 is equal to the limit from the right, which is 2, which is the exact value, but the exact value is 1. So that's false. My answer choice is C. All right. Hopefully that makes sense. Let's move onwards where I look at continuity algebraically. And actually, we sort of already covered that. So we are just going to resolve this. All right. If the function f is continuous for all real numbers, and if f of x is equal to x squared minus 4 divided by x plus 2, when x does not equal -2, then f of -2 is equal to what? All right. So this is saying the function f is continuous for all real numbers, right? Well, there's sort of an issue here because x squared minus 4 divided by x plus 2 is not continuous at x equals -2. Why? Well, when I plug in -2, I would get -2 plus 2, which is a divide by 0 error, right? So the exact value doesn't exist. Impossible for continuity. Right? If my exact value doesn't exist, Right? My exact value, it doesn't even exist. How can it be continuous? How can they all be equal to each other? All right, so how do I make this continuous then? Well, let's take a look at x squared minus 4 divided by x plus 2. You'll notice I can factor this. So it's x plus 2. The top, anytime I see something I can factor, it's usually a good idea to factor. So I'm going to say good idea to factor if you can factor, usually. So on the AP exam, just if you can factor, it's probably a good idea to factor. So x squared minus 4 turns into x plus 2 times x minus 2. You'll notice the x plus 2's, they cancel out. So I'm left with just x minus 2. So f of negative 2 now is no longer going to be a divide by 0 answer. It's going to be negative 2 minus 2, which is equal to negative 4. So it actually is continuous at negative 4. Okay, hopefully that makes sense. All right, last one on the continuity. So these sorts of problems, I feel like they're probably relatively the most difficult, but the same concept applies. So for the function defined above, for what value of b is f continuous at x equals 2? Well, remember the limit as x approaches the, limit from the left equals the limit from the right equals the exact value. Right, well, what's my limit from the left? Well, from the left, so you can imagine, actually this can be confusing because you're looking for inequalities. Well, what is the left side? Well, this is saying at 2, it's this function, but everywhere else, it is this function. All right, so my limit from the left uses this function, as does the limit from the right. Everywhere besides 2 uses this function. So let's plug it in. Limit from the left is going to be this x squared. And actually, what do I know already? I'm just going to write this in one step. My x is 2, right? So 2 squared minus 7 times 2 plus, is that a 10? Good, plus 10 divided by b times 2 minus 2 is equal to, the limit from the right is actually this exact same thing. So I'll just copy and paste it, right? Because from the right, it's also this function. And that's equal to the exact value, which is supposed to be equal to b. All right, so this equation must be true. I just need to solve for b. Well, one thing you'll notice first, 2 minus 2 is actually just 0, right? 0 times b is also 0. So I have a divide by 0 error. So how can something be equal to that then? Because divide by 0 means it's undefined. I'm not allowed to do that. That makes my equation not work, right? So that's the first thing I notice. So I'm going to go back to my equation and think sort of like this one. I got a divide by 0 error. How can I make this not have a divide by 0 error? Well, what I'm going to do is factor this. So the top, x squared minus 7x plus 10, this factors to x minus 5 times x minus 2. All right, the bottom is b times x minus 2. Well, what do I notice? My function can cancel out the x minus 2's, which means it's no longer going to be this. My left function is actually x minus 5 divided by b, which is, in this case, 2 minus 5 divided by b. So 2 minus 5 divided by b is equal to the same thing from the right. So 2 minus 5 divided by b is equal to b. Well, these two are identical, so it's redundant. So I'm just going to simplify my equation. It's 2 minus 5 divided by b is equal to b. This simplifies to 3 divided by b is equal to b, which simplifies to, I'm going to multiply both sides by b, so 3 is equal to b squared. I solve for b, so b is equal to square root of 3. All right. Now, looking at my answer choices here, you will see that root 3 is actually not an option. So in this case, I'm going to put my answer choice as E. Although this was a weird question, they really should have a root 3 option. So for the intents and purposes of this, I'll take E as the correct answer. All right, cool. We are going to now move on to the last topic, which is intermediate value theorem, right? And here you can see the notes for intermediate value theorem right here, but I'm going to type it out as well. So intermediate value theorem, right? So what does intermediate value theorem do? It basically guarantees a specific y value. And how does it do this? Well, it has some requirements. Requirement 1 is that the function must be continuous on the interval a to b, right? If the function is continuous on the interval a to b, that means all y values between, right, between when I plug in a and b, so f of a, which is a y value, and f of b are guaranteed, right? So basically what this saying is here, if you look at the graph here, between, my function is continuous, first of all, so it has to be continuous. So continuous, you must establish that. So if my function is continuous between a and b, which it looks like it is, then all y values between f of a and f of b are guaranteed. So f of a is the y value I get when I plug in a, so that's f of a, and f of b. Everything between these two values is guaranteed, which means k is guaranteed, right? I will say other y values are possible, right, but not guaranteed. Right, so it's not that the other y values are not possible. They're still possible, but they're just not guaranteed. All right, so let's answer this. Let f be a continuous function on the closed interval from -2 to 7. If f of -2 is 5 and f of 7 is -3, then the intermediate value theorem guarantees that. Okay, well, first of all, guarantees a specific y value. So here, this is giving me that a derivative is equal to 0. So that's guaranteeing dy dx. Well, that's just not true. My intermediate value theorem has nothing to do with derivatives. So right off the bat, I'm going to eliminate it. All right, eliminate a and b. All right, well, here, C and D both are saying that the value of 0 is guaranteed. Well, if my function goes from the y values, so between -2 and 7, these are x values, right? X values. My y values are 5 and -3. Well, 0 is between those, so yes, my y values of 0 are guaranteed. Now it says for at least one c between -3 and 5 or between -2 and 7. Well, 1c, when they say 1c, this is my c value. Right, so c is a x value. So it's saying between the x values, for example, between a and b, my c right here is guaranteed. That happens between my x values of -2 and 7. So basically, my answer is D. Y is equal to 1 when, but for at least an x value, sorry, y is equal to 0 at least 1 point between x values of -2 and 7. All right, hopefully that makes sense. Next problem. The function f is continuous on the closed interval from 0 to 2 and has the values that are given in the table above. The equation f of x is equal to 1/2, so this is a y value. Must have at least 2 solutions, so 2 guarantees on the interval from 0 to 2. These are x values if k is equal to what? So k here, you'll see, is a y value. All right, so my function goes from y values of 1 to something to 2, right? And I want to guarantee 1/2. Well, think about it this way. I have a y value of 1/2. So I'll say y is equal to 1/2. But I want to guarantee at least 2 times I cross this, right? Well, I start off at 0, 1. So I start off right here. I'm going to say I start off at y equals 1. So I start off right here, and I end up at y equals 2. So I go from here to here, right? Here to here. How do I guarantee 2 solutions of me crossing this red line of 1/2? Well, I need to go below the line and come back up on the line. So the only option that allows me to do that is 0, right? Because if I were to go to 0, you'll see I start here, I go down to this purple line, and I go up to the green line. I cross the red line 2 times. All right. Last intermediate value theorem question. Let g be a continuous function on the closed interval. Cool, so it's continuous, right? Actually, I should have noted that here. The function f is continuous. All right, g is a continuous function on the closed interval from 0 to 1. Let g of 0 equal 1 and g of 1 equals 0. Which of the following is not necessarily true? All right, so g of 0 is equal to 1. So 0 is an x value, 1 is a y value, 1 is an x value, 0 is a y value. Which of the following is not necessarily true? Okay, well, if I were to say, put this, before I even look at my answer choices, what does this guarantee? All right, so it's continuous, so I can use IVT. And remember, all my guarantee specific y values. So all y values between 1 and 0 are guaranteed. On the interval 0 to 1, these are my x values, right? So 0, 1. Okay, so let's see which one of these matches. There exists a number h in 0 to 1 such that g of h is greater than or equal to g of x for all of x in 0, 1. This has nothing to do with intermediate value theorem. Also, if you were to, all this is saying, answer choice A is saying, that there's a sort of maximum, right? G of h is greater than or equal to g of x. All right, anyway, basically you can eliminate almost all these answer choices, except for which is not necessarily true, is D, right? 3/2, because 3/2 is not a y value between 1 and 0, right? So 3/2 is possible, but not guaranteed. So it's not necessarily true, not necessarily true, essentially. All right, hopefully that makes sense. Finally, I'm going to attempt these last 2 problems. So I took some notes here, but show that f is continuous at x equals 0. All right, so for a function to be continuous, the limit from the left must equal the limit from the right, must equal the exact value. So let's do that. Well, the limit from the left would be this function. So y minus 2 sine of x. What is x in this case? Well, x is 0, so it's 2 sine of 0. I'm going to turn this to radians. All right, is equal to the limit from the right. Well, from the right, it's this function, right? Because x is greater than 0, so that's from the right. So it's e to the -4 times 0 is equal to the exact value. Well, what is that exact value? That exact value is going to be when x is equal to 0. So it's actually sort of redundant. It's this equation again. All right, 1 minus 2 sine of 0. Sine of 0 is 0, so it's 1 minus 0 is equal to, this is e to the 0. E to the 0 is, anything to the 0 is 1. It's equal to 1 minus 0. So it's 1 is equal to 1 equals 1. This is continuous. This is continuous. All right. Hopefully that makes sense. Next question. Let g be the function defined by this. Is the function g continuous at x equals -3? Okay, let's use my limit definition again. Right, it says use the definition of continuity to explain your answer. All right, my limit from the left. To the left of -3, this might be more confusing, but left of -3, you just look at this part, right? X is to the left of -3. All right, so to the left of -3, I'm going to use the function f of x. So really it's f of -3. has to be equal to the limit from the right of -3. This is to the right of -3. That's going to be x plus 7, so -3 plus 7 is equal to the exact value. The exact value is when x is equal to -3, so it uses that function again. F of -3. All right, well, what is f of -3? You might say, well, they give us f, so that's nice. So I'm just going to plug -3 into that function. So square root of 25 minus -3 squared is equal to -3 plus 7 is 4, is equal to, this is redundant, but I'll write it just so we have that. And this again. All right, that's square root of 25 minus 9 is equal to 4. Okay, I'm just going to eliminate, not write that again, because I don't need to show that, because it's the same thing. That's square root of 16 is equal to 4. And that's 4 is equal to 4. So 4 is equal to 4 is equal to 4 is equal to 4. This is continuous. Is continuous. One thing I will note for these problems, must show work using limits. All right, cool. That is my video for today, and hopefully that helps you answer. I mean, you can use this, copy it down, use it as a guide to answer every single problem on the first packet. Thank you, guys.